Imagine a vast, empty region of space, devoid of all matter and energy, except for the mysterious force we call dark energy. Even in this seemingly empty void, the laws of quantum mechanics dictate that virtual particles are constantly popping in and out of existence. These are not just any particles, but particle-antiparticle pairs, a fleeting dance of matter and its opposite, antimatter. Normally, they borrow energy from the quantum vacuum for a fleeting moment, then find each other and annihilate, returning the borrowed energy in a perfect silent cancellation. But in this dark energy-dominated region, something extraordinary happens. The intense, pervasive dark energy acts like a colossal, irresistible force, a cosmic wedge. As a virtual matter particle and its corresponding antimatter particle flicker into existence, this dark energy violently thrusts them apart, tearing them from their mutual annihilation. They are flung away from each other with such incredible force that they cannot recombine. Instead, each now isolated particle, one of matter, the other of antimatter, becomes a seed, alone. Yet supercharged by the conditions of their birth and separation, they begin to expand rapidly, feeding off the ambient dark energy. Each particle, in essence, acts as its own singularity, a point of unimaginable density and temperature. From the matter particle, a universe dominated by matter begins to unfurl. Simultaneously, from the antimatter particle, a twin universe, overwhelmingly composed of antimatter, starts its own independent expansion. This is the birth of not just one, but two distinct universes, born from a single quantum event but forever separated by the primordial push of dark energy. Two big bangs, one we might call the matter bang, the other the anti-bang, erupt, each spawning its own galaxies, stars, and potentially its own forms of existence, all while the pervasive dark energy continues to accelerate their outward, independent journeys, and the separation between these cosmic twins. This process could be happening all over the cosmos, giving rise to countless pairs of universes. It's a mind-bending concept that challenges our understanding of reality, but it's also a testament to the boundless creativity of the universe. You might wonder, if these paired universe-birthing events are happening, why don't we see evidence of antimatter universes or these genesis events in our own cosmic neighborhood? Our universe, as we know it, is filled with galaxies, stars, planets, and vast clouds of gas and dust, predominantly matter. This abundance of existing matter and energy creates a cosmic noise, a complex environment that would disrupt the delicate quantum dance needed for these virtual particle pairs to be so perfectly separated and to individually ignite new universes. It's like trying to isolate two specific interacting raindrops in the middle of a torrential downpour. The ambient conditions are simply not conducive. For these multi-bang twin universe events to occur, they would likely need to happen in regions of space far beyond our observable universe. Imagine the entirety of what we can see as a tiny island in a vast, dark ocean. It's in the immense, ultra-low-density waters beyond our horizon, where dark energy reigns supreme and both matter and antimatter are virtually absent, that these cosmic seeds, these particle-antiparticle pairs, could be torn apart to take root. The expansion of the universe itself contributes to this, constantly pushing these potential birthing grounds further away from us, beyond our current and perhaps even future observational reach. The violent initial separation also ensures these twin universes expand away from each other, making direct interaction or observation across their boundaries exceptionally unlikely. Even though the genesis of these new universes isn't from a traditional, universe-encompassing singularity, as in the standard Big Bang model for a single cosmos, each initial virtual particle, the matter 1 and the antimatter 1, at the moment of its dark energy-driven inflationary expansion, would itself be a point of incredible density and heat, a singularity in miniature. Each microscopic point contains all the potential for a new, distinct cosmos, one of matter, one of antimatter. As each initial particle singularity expands, driven and fueled by the surrounding dark energy, it rapidly creates more and more particles of its own kind matter in the matter universe, antimatter in the antimatter universe. This cascading creation of mass energy and the subsequent rapid expansion within each separated domain would be very similar to the Big Bang event that we believe started our own universe, just initially on a smaller duplicated scale. It's like twin cosmic sparks, each igniting its own colossal fire. And how could such mini Big Bangs grow? The surrounding dark energy acts as a relentless engine for each of them, a constant source of fuel, causing their individual expansions to accelerate. Over unimaginable timescales, this could lead to a runaway effect for both. Each initially small expansion could grow into a colossal event, potentially rivaling the scale of our own universe, forming two vast, new, and oppositely natured cosmic structures. It's akin to twin snowballs rolling downhill in opposite directions, each gathering speed and accreting more mass, growing ever larger, propelled by the same unseen force of dark energy. This theoretical framework, while speculative, doesn't necessarily contradict our current understanding of fundamental physics. Rather, it attempts to extend it. Field theory, a cornerstone of modern physics, describes particles as excited states, or ripples, in underlying quantum fields that permeate all of space. In this multi-bang theory, the virtual particle-antiparticle pairs that appear due to dark energy could be seen precisely as these fluctuations in the quantum fields. When these fluctuations, amplified by the unique conditions of an energy-dense but matter-empty void, are violently separated by dark energy, each distinct particle can then trigger the expansion of space itself within its own domain. This resonates with the cosmological concept of inflation, a period of super-rapid expansion thought to have occurred in the very early moments of our own universe, now applied to the genesis of twin universes. Particle physics, which governs the behavior of these fundamental constituents, describes the fleeting existence of virtual particle-antiparticle pairs. They pop in and out of existence, usually annihilating too quickly to have lasting effects. However, in our proposed scenario, the overwhelming influence of dark energy provides the crucial kick to violently separate these pairs before annihilation. This separation and subsequent energizing allow each to persist, expand, and initiate its own cascade of particle creation. It's as if dark energy performs a cosmic sorting and powering up, altering their usual shared fate into two independent destinies. This particular theory, envisioning the birth of twin matter and antimatter universes, if it holds any truth, could offer potential answers to some of the most profound mysteries in cosmology and particle physics. Firstly, the origin of dark energy itself, and its counterpart dark matter, remains one of the biggest puzzles. Perhaps these paired multi-bang events, and the nature of the empty space that allows their violent separation, are intrinsically linked to the properties of dark energy, and could even provide a mechanism for the creation or distribution of dark matter within each respective universe. Secondly, the matter-antimatter asymmetry. Why our universe is overwhelmingly made of matter when the Big Bang should have produced equal amounts of matter and antimatter is a long-standing enigma. If universes are born from particle-antiparticle pairs, where the matter particle seeds a matter-dominated cosmos, like ours, and its twin antimatter particle is violently flung apart to seed a separate, parallel antimatter-dominated universe, this provides a natural and elegant explanation for the observed imbalance in our own local universe. Our Big Bang might have had a big anti-bang counterpart, its antimatter twin, now forever separated and expanding independently due to that initial forceful push from dark energy. Finally, the theory inherently supports the concept of a multiverse, not just as a mathematical curiosity, but as a physical consequence of ongoing processes where matter-antimatter pairs are continually being separated to form new, distinct cosmic domains. However, this framework also brings forth a new set of challenging questions. What are the precise conditions required for these virtual particle-antiparticle pairs to be so effectively separated and to each transition into universe-birthing events? How frequently do such paired events occur across the entirety of space? What determines the ultimate fate and physical laws within these newly formed, oppositely natured universes? And crucially, how could we ever hope to find evidence for our antimatter twin or other such paired universes, given their violent initial separation and subsequent independent expansions? While directly observing our antimatter twin universe, or other such paired events, is likely far beyond our current capabilities due to the vast distances and the nature of their separation, there might be indirect ways to search for clues. To get the data we need, scientists could look for subtle, large-scale anisotropies or unusual patterns in the cosmic microwave background radiation, the afterglow of our own Big Bang, that might hint at extremely large-scale structural influences, though distinguishing this from other cosmological models would be incredibly difficult. Highly sensitive gravitational wave observatories could, in principle, detect faint ripples in space-time originating from these incredibly energetic distant genesis events, if their effects could somehow propagate or be inferred across cosmic scales. Mathematically, describing such a paired event and subsequent individual expansions is a formidable task, but we can outline the core concepts for each universe. The expansion of one of these mini-Big Bangs, either the matter or antimatter one, could, in a simplified form, be represented by an equation like AT 1 plus T 2. Here AT is the scale factor, representing the size of one of the new universes, for example, our matter universe, at a given time, T, after its initial separation and ignition. A would be its initial infinitesimally small size, related to the scale of a single virtual particle. E is Euler's number, the base of natural logarithms, indicative of exponential growth. H represents the initial expansion rate for that universe, critically dependent on the local density of dark energy that fueled its birth. The term, 1 plus T 2, attempts to model a transition for that universe. T0 is a characteristic timescale. Initially, for T0, the expansion is predominantly exponential, E hat. As T becomes comparable to or larger than T0, the second term becomes significant, potentially moderating the pure exponential growth and transitioning it towards a different expansion regime as the internal dynamics of that newly forming universe, like its own matter or antimatter and radiation density, start to play a role. We can estimate AO from quantum theory. We have measurements of the expansion rate of our own universe, which gives us some understanding of how dark energy behaves, offering clues for H. However, T0, the timescale for the transition, and the precise interplay of the internal energy components of these new, separate universes remain deeply theoretical. The key addition to the model is that two such equations would run in parallel, one for the matter universe and one for the antimatter universe, both originating from the same initial dark energy-driven separation event. Pushing the boundaries of our understanding of the cosmos, even with theories as speculative as the birth of twin matter-antimatter universes, is fundamental to human advancement. If such processes are indeed occurring, they represent a new frontier in physics. Could we, in some distant future, understand the conditions for these violent separation and dual genesis events well enough to even predict them? Could the immense energies involved, or the novel physics they might reveal about the interplay of matter, antimatter, and dark energy, ever be harnessed or applied in ways we can barely dream of today? Perhaps the greatest application is the expansion of our cosmic perspective. To know that our universe might be one of a pair, its existence mirrored by an antimatter counterpart, born from the subtle quantum jitters of the void and the forceful intervention of dark energy, redefines our place in the grand scheme of existence. It encourages us to keep questioning, exploring, and striving to comprehend the ultimate nature of reality and the fundamental symmetries that might govern it. The pursuit of these answers, regardless of their immediate applicability, is a hallmark of human curiosity and our unending quest for knowledge.